Let's now investigate the most common forms of energy that have been identified to exist in the universe. As stated previously, there are four basic forms of energy: kinetic, gravitational, electric, and nuclear. So let's talk about kinetic energy. Kinetic energy is possessed by all moving objects and is equal to 1/2 the mass of an object multiplied by the square of the object's velocity. So the kinetic energy, if you recall from physics, is equal to 1/2 mass times velocity squared. Very famous physics 1 kind of equation, right? So kinetic energy equals 1/2 mass times velocity squared. So we could carry this out and we'll find out the SI units result in mass, which is kilograms, velocity is meters per second, right? We square that so we get kilogram meters per second squared equals joules, as we would expect, right? The internal kinetic energy of a material determines its temperature due to the constant vibrations of atoms bouncing around and molecules that make up all the matter. This form of kinetic energy is often referred to as thermal energy or heat. Gravitational energy is a result of the gravitational pull that exists between any two objects. They'll exert an attractive force on one another. When referenced to Earth, any object lifted to oppose gravitational attraction, if I lift it up, it's going to gain what we call potential energy, equal to the mass of the object multiplied by the force of the gravitational attraction multiplied by the height of the object above the Earth. Often we write this as potential energy equals mass times gravity times height. The SI units here are going to be kilograms for mass. Gravitational attraction is, again, it's meters per second squared. And height is measured in meters. So we get kilograms meters squared per second squared, or joules, right? So great. Potential energy can also be described as force times distance, where the force acting on an object is called weight and is found by multiplying the acceleration due to gravity by the object's mass, right? Electrical energy is associated with the cloud of electrons that exist in every atom. When atoms bond to form molecules, the natural charge distribution of the electrons is changed. When they come together, the distribution of electrons changes, and energy is stored in the form of chemical energy. When a fuel, such as coal or petroleum, is burned, the energy stored in these chemical bonds is converted into thermal energy, essentially a conversion of electrical energy into kinetic. More commonly, though, electrical energy is associated with electricity, which is the flow of electric current in a conductor. Typically, an input fuel is burned and used to produce steam. The steam pressure is then used to drive a rotating turbine, which in turn drives an electrical generator. When the generator is connected to an electrical circuit that includes wires and some sort of load or a device that will consume power, current will flow. The electrical energy is then converted into heat, light, or motion, depending on the type of load connected. Electricity is what we call an intermediate form of energy with unique properties that make it extremely valuable. It can be produced at one location and transmitted to another location almost instantaneously. It can be easily transduced to other energy forms and can be used to do useful work, and by that we mean we can use electricity to have rotary motion in motors. We can use electricity to create sound in speakers. We can use electricity to produce heat in heating systems. We can use electricity to produce light. We can transduce it very easily. It can be easily delivered and controlled by systems of wires and control devices. So unlike some of the other forms of energy, electrical energy is very easy to route and control. However, the major deficiency of electric energy in the form of electricity is that we don't have any way to store it. Another way an electric energy can be carried is by which is called electromagnetic energy, which exists in the forms of solar energy, X-rays, visible light, radio waves, microwaves. So all these other types of energy forms, cosmic rays, things like that, that is another form of electrical energy. Finally, we come to nuclear energy, right? Nuclear energy. This is the energy associated with the energy stored in the protons bound inside of the nucleus of all atoms. When an atom undergoes nuclear fission, The nucleus of an atom splits into smaller parts. These protons come apart. It'll produce free neutrons and photons, which are sometimes called gamma rays, and it will also release a very large amount of energy. This is the process that's used in nuclear power plants, atom smashing, where the energy release produces heat to create the steam that is then used to turn the turbine generators. Nuclear energy is also the source of the energy emitted by the sun, which is constantly undergoing a different process, nuclear fusion, where two or more atomic nuclei are colliding at high speeds and joining to form a new type of atomic nucleus and to release energy. The U.S. total energy consumption in 2011 was 97.3 quadrillion BTUs. I'm going to write that down. 97.3 quadrillion. A quadrillion is 10 to the 15th BTUs. Often this is called a quad. Quad are very common units when dealing with large amounts of energy, such as on a national scale. This is about 285 trillion kilowatt hours. 28.5 trillion kilowatt hours. Trillion kWh. So it's a huge number, right? But as stated earlier, we cannot create or consume energy. So where did all this energy come from, and what forms was it converted to? Because this is total energy consumption I'm talking about here. Energy production and usage in the United States is tracked using what are called energy flow diagrams. On such energy flow diagrams, energy inputs are depicted as tails here entering from the left. Energy transactions are represented as the body of the diagram. And energy usage is represented as arrows leaving from the right side of the diagram. So these arrows coming out are from the right diagram. So this figure shows the total energy flow for the U.S. in 2011. The left-hand side again represents all the energy inputs into the system. This includes energy imports, energy production, stock change, adjustments, losses, and unaccounted for energy. Here we can see that 78.10 quad of energy was produced domestically. So that's this, domestic production. So if we look at coal, nat gas, crude oil, natural gas liquids, nuclear electric power, renewable energy, our domestic production, all that adds up to 78.1 quad of energy. And then we also imported 28.59 quads of energy that came from mostly from petroleum. Excuse me, the vast amount from petroleum. The right-hand side of this figure here represents all the energy outputs of our system. A distinction here is made between exports and domestic consumption. So what we see is that 10.6 quads, 10.36 quads of energy were exported, and then 97.3 quads were consumed domestically, meaning that we're a net energy importer in the United States.